Hello everyone. Once again welcome to my YouTube channel Physics with Dr. Sanjay Bhargav. In our part 1 of the video Motion in One Dimension, we have dealt with distance, displacement, speed, velocity, instantaneous and average speed, instantaneous and average velocities, and certain type of important graphs relating distance time, displacement time, speed time and velocity time. In this video, in continuation of our earlier video, we'll discuss about acceleration, average and instantaneous acceleration. We'll then calculate the equations of motion, which include velocity time relation, displacement time relation, velocity displacement relation and distance traveled in the nth second. We'll also address the problem of motion under gravity. We'll also talk about relative velocity and try to discuss certain important aspects of problem solving in two-dimensional problems. We begin with acceleration. How do we define acceleration? We define acceleration as rate of change of velocity with time. So we have uniform acceleration. So what is uniform acceleration? An object is said to have uniform acceleration if its velocity changes by equal amounts in equal intervals of time. So in case of uniform acceleration, a body must have equal change of velocity in equal intervals of time. Acceleration is supposed to be a vector quantity as it both has magnitude and direction. The SI unit is meter per second square and the dimensions are L1 t power minus 2. The acceleration can be positive, negative and zero. Positive acceleration means velocity is increasing with time, while negative acceleration, also called as retardation, means velocity is decreasing with time. The negative acceleration is also referred as retardation or deceleration. A body having zero acceleration is one where velocity is constant, that is a state of uniform motion. So when the velocity does not change with respect to time, it's the state of uniform motion, and in that case of uniform motion we have zero acceleration. Now what is our imagination or perspective on acceleration? In case a particle has zero velocity at any instant, it does not necessarily mean that it has zero acceleration at that instant. What I am trying to say is, a particle can have zero velocity, but it does not necessarily mean that it should have zero acceleration at that instant of time. Let us pick up an example. When a particle is thrown vertically upward, then at the highest point it has zero velocity, but acceleration at that instant is equal to the acceleration due to gravity g. So zero velocity is not a guarantee of a zero acceleration. Though velocity and acceleration are related to each other, they have their own distinct meaning. Velocities, it tells us how fast and in what direction the object is moving, while acceleration tells us how its speed and direction of motion are changing. So what is the information provided by the velocity? It tells me how fast an object is moving and in which direction is the object moving. While what does the acceleration gives? It tells how its speed and the direction are changing with respect to time. So both the quantities, though may seem to be related, but have their own individual existence. If the acceleration is in the direction of a velocity, that is, the sign of acceleration is same as the sign of velocity, then the speed of the particle increases. If the acceleration is in a direction opposite to that of velocity, then sign of acceleration is opposite to that of velocity, then the speed of the particle decreases. So it tells us when does the speed of a particle increase and under what condition the speed of the particle decreases. If the acceleration and the velocity have the same direction, then the speed of the particle increases. If the acceleration and the velocity have opposite direction, then I can say speed of the particle would decrease. Thus, sign of acceleration of a particle does not tell us whether the speed of the particle is increasing or decreasing. So a very important point to be taken care of, that sign of the acceleration, like acceleration due to gravity is acting in the downward direction, we put a negative sign with it, but that sign does not tell us whether the speed of the particle is increasing or decreasing. We just provide an example to it. Acceleration due to gravity acts in the downward direction and is taken negative. For a particle falling under gravity, g is negative, but it increases the speed of the particle. When the particle is thrown up, negative g causes a decrease in the speed of particle. So calling negative acceleration at deceleration is not justified. Just we will identify it on the basis whether the speed is increasing, we call it as acceleration. If the speed is decreasing, we will call it as deceleration. Acceleration and deceleration not to be decided on the basis of the sign associated with the acceleration. Right? A very important thing that need to be taken care of, where we make certain common mistakes. Now, we have a graph here. It's a position time graph. On this axis, we are plotting position, and on this axis, we are plotting time. Then the graph curves upward when the direction of acceleration is same as that of velocity, like in this case. The direction of acceleration and the direction of velocity is the same. We have curve A. Then the curve downwards when the direction of acceleration is opposite to that of velocity, this one. Here acceleration and velocity are in the opposite direction. So what is happening? Velocity is decreasing with time. Here velocity is increasing with time. For zero acceleration, the graph is a straight line, which is shown here as a curve B. So you have to obtain different informations under different conditions. Average and instantaneous acceleration. Let us first define average acceleration. It is defined as the ratio of change in velocity to the time interval in which the change takes place. So average acceleration, change in velocity upon the time interval for the change. It is equal to v2 minus v1 upon t2 minus t1. Average acceleration would be delta v by delta t as usual. This is the same way of description for average velocity and average speed. Instantaneous acceleration. It is defined as the instantaneous rate of change of velocity with time and is the limit of average acceleration as the time interval delta t approaches 0. So instantaneous acceleration is limit delta t tending to 0. Delta v by delta t can be written as dv by dt. Instantaneous acceleration is the time derivative of instantaneous velocity. Acceleration is equal to dv by dt, and v can be written as rate of change of displacement with respect to time. So acceleration is also equal to d2x by dt square. Acceleration of a particle at any instant is the second derivative of position x with respect to time. So we need to determine average and instantaneous accelerations graphically also. Let us calculate average and instantaneous acceleration from the velocity time graph. The average acceleration during any time interval is equal to slope of a straight line joining these 2 points on a velocity time graph. So this represents velocity time graph On the x-axis, you are plotting time. On the y-axis, we are plotting velocity. At the point A, the velocity is v1 at the time t1. At the point B, velocity is v2 at the time t2. The slope of the straight line AB is equal to delta v by delta t. So average acceleration is delta v by delta t. Average acceleration is nothing but the slope of a straight line joining 2 points on velocity time graph. Instantaneous acceleration, the concept remains the same. The instantaneous acceleration at any point is equal to the slope of the tangent to the velocity time graph at that particular point. Again, the logic is same. When the point B approaches A, then delta t tends to 0. In this condition, the straight line AB would become tangent to the graph at point A. So, limit delta t tending to 0, delta v by delta t would be equal to limit delta t tending to 0, the slope of a straight line AB, which would be nothing but slope of tangent at point A. Limit delta t tending to 0, delta v by delta t can be mathematically written as dv by dt, which is nothing but instantaneous acceleration at point A. So what is A? It is equal to slope of the tangent at point A. So we have proved here once again that instantaneous acceleration would be nothing but slope of the tangent at point A. Now let us derive the kinematics equations of motion in a straight line under constant acceleration by calculus method. First we pick up is velocity time relation. We consider a particle moving with uniform acceleration A. A can be written as dv by dt or dv can be written as a dt. At the time t is equal to 0, velocity would be equal to initial velocity u, and at the time t, the velocity is v. Now integrate with proper limits. What do we get? Integration dv from u to v would be integration a dt from 0 to t, or integration dv is v, and the limits of integration from u to v. A integration of dt is once again t from 0 to t. Apply limits of integration. V minus u is equal to a into t minus 0. So v would be equal to u plus at. This is known as velocity time relation. What is the utility of velocity time relation? It helps to calculate velocity of an object moving with uniform acceleration after time t. Now, the second equation of motion, that is displacement time relation. We consider a particle moving in a straight line with uniform velocity v. So v can be written mathematically as dx by dt, or dx can be written as v dt. Just now we have put as v is equal to u plus at. So replace v by u plus at. Dx can be written as u dt plus at dt. At t is equal to 0, x is equal to 0. At the time t is equal to 0, x is equal to s. So integrate both the sides with proper limits. Integration of dx 0 से s. Integration u dt from the time 0 to t. Integration a t dt from 0 to t. U is constant, so can be taken out sign of integration. Similarly, a is constant, so take out of the sign of integration. Integration of dx is x. Limits of integration 0 to s. U is a constant, integration dt would be t. The limit 0 to t. Integration of t would be t square by 2 and 0 to t. Just substitute the limit. It is upper limit minus lower limit. So we get the equation s is equal to ut plus half at square. What information does it provide? It provides me the displacement time relation. And where it is used? It is used to calculate total displacement of an object moving with uniform acceleration after time t. Now, the third equation is the velocity displacement equation. We know a would be equal to dv by dt. You can multiply and divide by dx. So dv by dx is into dx by dt. Dx by dt is nothing but velocity. So just cross multiply. What do we obtain? A times dx is v into dv. Now select the limits properly. At x is equal to x0, the velocity is v, and when x is equal to x, velocity is, so v, it is u. Integrating with proper limits, a dx from x0 to x, u to v. So a is a constant, take out of the integration sign, integrate dx from x0 to x. Similarly, integrate v from initial velocity and final velocity. Integration of dx is x, limits ranging from x0 to x. V square by 2 is the integration, and u to v is the limits. So it is twice a into x minus x0 is v square minus u square. Rearrange the terms and put x minus x0 as s. What do I get? S, v square would be equal to u square plus 2as. This is basically velocity displacement relation and is used to calculate velocity of an object moving with uniform acceleration after traveling a distance s. Now another important relation is distance covered in nth second. Like we are faced with a question, what is the total distance traveled in the 5th second? Then we need an answer to it. For that, we'll derive a general relation to handle such situations. We consider a particle moving in a straight line with uniform acceleration. U would be initial velocity, A is the uniform acceleration, and what is Sn? Distance traveled or covered in n seconds, and Sn minus 1, distance traveled in n minus 1 seconds. Let us utilize the relation S is equal to ut plus half at square. So in n seconds it is un plus half an square. In n minus 1 seconds it is u n minus 1 plus a by 2 into n minus 1 ka whole square. What is the distance traveled in the nth second? It would be total distance traveled in n seconds minus total distance traveled in n minus 1 second. Just subtract the two equations. Rearrange the terms and we obtain here S nth would be equal to u plus a by 2 into 2n minus 1. So these are four important results. V is equal to u plus at, S would be equal to ut plus half at square, v square would be equal to u square plus 2as, S nth would be equal to u plus a by 2 into 2n minus 1. Which would be utilized under various situations to handle the practical and numerical problems. Now let us focus on motion under gravity. Now motion under gravity is a case of one-dimensional motion with constant acceleration. Here acceleration due to gravity g is constant and directed vertically downward. The frictional force due to air is absent, that is motion takes place in a vacuum. So g acting vertically downward, a is equal to plus g, downward direction, and a is equal to, if I take origin at the top, then the downward direction would be taken positive. If I am at this point, then a would be equal to minus g. So all the signs to be decided, where do we pick the origin from? That is how to handle such situations. We will define a sign convention for us, which just simplifies the things for us. Initial position of a body is taken as the origin. For a freely falling body, the vertically downward direction is taken positive. For a body projected vertically upward, the upward direction is taken positive. So under free fall, a would be plus g, and for objects projected upward, a would be equal to minus g. Motion of body falling freely under gravity. Let a body fall from rest from a height h. Here u is equal to 0, s would be equal to h, and a would be equal to g. So from this equation we obtain v is equal to gt. I can calculate the time of fall as v upon g. From this equation u is 0, so h would be equal to half gt square, so the time taken would be equal to under root 2h upon g. From this equation v is equal to u square plus 2gh, u is 0, so v square would be equal to 2gh, so v would be equal to under root 2gh. Height in the nth second would be 2n minus 1 into g by 2. assuming initial velocity u to be 0. Motion of a body projected upward. Let the body be projected upward with an initial velocity u and h be the maximum height attained after time t. When it comes to rest, for a moment the velocity becomes 0, s is equal to h and a would be minus g. In this situation, u would be equal to gt, h would be equal to ut minus half gt square and u square would be equal to 2gh. From equation 3 and 7, what do we find? The value of initial and the final velocity is the same, that is under root 2gh. It proves the speed with which a body is projected is equal to the speed with which it returns to the point of projection. As u is equal to v, what we can say from equation number 1 and 5, the time taken to go up a height is same as time taken to fall through the same height. From equation number 1, velocity is directly proportional to time. From equation number 2, h is proportional to t square. The heights through which a body falls from rest in time t, 2t, 3t are in the ratio 1 square, 2 is to 2 square is to 3 square, that is 1 is to 4 is to 9, a square of integers. From equation 3, v is directly proportional to h. From equation number 4, h nth is directly proportional to 2n minus 1. So it answers the question, the height through which a body falls from rest in first, second and third second are in the ratio 1 is to 3 is to 5, that is in the order of odd integers. This result is known as Galileo law of odd numbers. We can also derive the equations of motion by graphical method. We consider an object moving along a straight line with initial velocity u and uniform acceleration a. The velocity time graph is shown here. On this graph, of y-axis we have taken velocity, here time, initial velocity at point A is u and the final velocity at point B is v. At t is equal to 0, v is equal to u. At t is equal to 2, t, v is equal to v. What is the slope of this graph? It would be BD upon AD. BC minus DC, that is v minus u upon t. So slope of the VT graph is acceleration. So I can put v minus u upon t as a. Rearranging, I get the first equation, v is equal to u plus at. Now I need to calculate what would be the distance that would be traveled in time t. It would be equal to area under velocity time graph. Now just look at the velocity time graph. This is AB. The area under this curve is equal to area of the triangle plus area of the rectangle. That is what we have represented as area of the trapezium OABCO, area of triangle ABD and area of the rectangle. So area of the triangle is half base into height and length into breadth. Substitute the physical quantities, rearrange, you will get S is equal to ut plus half at square. The distance travelled in time t would be equal to area of trapezium. And what is the area of trapezium? Half the sum of parallel sides into distance between parallel sides. So that is half u plus v into t. So u plus v would be equal to 2s upon t. Also v minus u is equal to at. Now multiply these two equations. What do we obtain? 2as is equal to v square minus u square. Rearrange, I'll get the equation v square would be equal to u square plus 2as. Thus we can obtain the equations of motion either graphically or by the calculus methods as according to our requirement. Hope you are enjoying the video on one-dimensional motion part 2. Once again, I request you to subscribe my channel. For those who have not subscribed till date, all videos that you like and enjoy, please comment and like the videos. Now moving ahead, we pick up another word, and that is relative velocity. We have already said rest and motion are relative and not absolute. A given object which is at rest with respect to a particular observer, but it may be in motion with respect to another observer. The velocity is also relative and not absolute. Thus, to describe velocity, we have to mention the observer with respect to which the velocity is being measured. The relative velocity of object A with respect to another body B, that is VAB, is the rate at which body A changes its position with respect to body B. We consider two objects A and B moving with uniform velocities VA and BB respectively. Let x0a and x0b be their position coordinates at the initial time t is equal to 0. x0a minus x0b is the displacement between the two bodies A and B at the time t is equal to 0. If xa and xb are the positions of coordinates at the time t, then xa would be x0a plus vat, xb would be equal to x0b plus vbt, xa minus xb would be x0a minus x0b plus va minus vb into t. The displacement between the two bodies increases by va minus vb into t during the time interval t. Relative velocity of A with respect to B is equal to displacement upon time, and the displacement is va minus vb upon t. The time cancels, so relative velocity va minus vab would be equal to va minus vb. Similarly, I can calculate what would be the relative velocity B with respect to A. So VBA would be VB minus VA. From equation number 2, 1 and 2, VAB is equal to minus of VBA. The relative velocity of A with respect to B is equal to negative relative velocity of B with respect to A. But the magnitude of VAB and magnitude of VBA is equal to V, where what does V represent? It is the relative speed between A and B. The relative speed between two bodies A and B moving in the same direction with same speed, with speeds VA and VB. So what is V same? It is equal to difference in the speed of two bodies A and B. Magnitude VA minus magnitude VB, or magnitude B minus magnitude of VA, depending upon the fact whether VA is greater than VB or VB is greater than VA. The relative speed between two bodies A and B moving in opposite direction with speed VA and VB is equal to, V opposite is equal to sum of the speeds of two bodies A and B, VA plus VB. Note, these equations are valid only in one-dimensional motion. Now let us analyze relative velocity from position time graph. We know that xa minus xb is equal to x0a minus x0b plus va minus vb into t. If va and vb are equal, then what will happen? xa minus xb would be x0a minus x0b. If the two bodies remain at constant separation, so the position time graph are parallel to each other, like here. They are parallel to each other. Since the velocities are equal, so the displacement at the time t is equal to 0 and at a later time is equal. Then we may have VA may not be equal to VB. Then one graph would be more steeper than the other. They meet at a point. For example, let us pick up VB is greater than VA. Then what will happen? Just look here. VB, the slope is more, and VA, the slope is less. They meet at this time t. So from the initial time t is equal to 0 to t dash, the separation decreases, and after t dash the separation once again increases. So we see the graphs meeting at point P at the time t dash. At t dash, body B overtakes body A. Before t dash, xa minus xb is positive, and after t dash, xa minus xb is negative. Now we'll handle certain typical problems that you come across in two-dimensional motion. We have an example 1. A man has to go 50 meter due north, 40 meter due east and 20 meter due south to reach a field. What distance he has to walk to reach the field? What is the displacement? Let us draw the figure for it. So it says 40 meter to the east. What is our concept of direction? This is north, south, east and west. So 40 meter east, 30 meter north and 40 meter to the east, 20 meter to the north. 50 meter north, 40 meter due east and 20 meter due south. So we are here 20 meter to the south, downward direction, 50 meter to the north, upward direction. Just arrange the vectors now. Actual distance traveled is from A to B, B to C and C to D. So it is 50 plus 40 plus 20 giving me 110 meter. When it comes to the displacement, then we have to use polygon law. So it would be AB vector plus BC vector plus CD vector, 50 j cap plus 40 I cap plus 20 minus of j cap, it is 40 I cap plus 30 j cap. So magnitude of the displacement would be 50 meter. If I need to calculate direction of the displacement, then direction of the displacement would be calculated by tangent theta, which would be given by from the figure DE upon AE, which is 3/4. And tangent inverse 3/4 would be 37 degrees. So we have magnitude of the displacement as 50 meter and the direction 37 degree with respect to the horizontal. Now let us take example number 2. A man walks at a speed of 6 km per hour for 1 km and 8 km per hour for next kilometer. Now average speed is total distance upon total time S1 plus S2 upon T1 plus T2. Total distance is 2 km. Time taken to cover S1 distance 1/6 hour and time taken to cover S2 distance is 1/8 hour. So just put in the relation S1 plus S2 upon T1 plus T2. So this would be 1 plus 1 2 and 1/6 plus 1/8, which on simplification gives 48/7 km per hour. So that's the average speed given by the harmonic mean of the two speeds. If the speed of the particle is v is equal to 10t square meter per second, then find out the distance covered between t is equal to 2 to t is equal to 5 seconds. We have v is equal to dx by dt. So dx would be equal to v dt. Integrate both the sides with proper limits. So dx from 0 to x and v dt from 0 to 2 to 5. So integration dx is x. Integration v can be replaced by 10t square. T square integration is t cube by 3. So we have 10/3, 5 ka cube minus 2 ka cube, and the total distance traveled is 390 meter. Then we have the example number 4th. The displacement time graph of two objects A and B is shown in the figure. Find the ratio of the velocities of the object. Velocity of the object would be slope of the displacement time graph, that is tangent theta. So velocity of object A upon velocity of object B, VA upon VB is equal to tangent of theta A upon tangent of theta B. Tangent 30 upon tangent 60. Tangent 30 is 1/√3 and tangent 60 is √3. So that is 1/3. So the ratio of the velocities VA and VB is 1:3. VA upon VB is 1:3. Example 5. Calculate the displacement and distance traveled from the graph. So area under velocity time graph would provide us a measure of displacement and distance. Distance traveled is area of the first square, second square and the third one. And let us calculate that area. The first area would be equal to 4 into 2. Second area would be 2 into 2 plus third area would be 2 into 2, that is 16 meter. But displacement is a vector, and in that case it would be area of the first minus area of the second because it is below the x-axis and then the area of the third one. So that gives me 4 into 2 minus 2 into 2 plus 2 into 2, and the total displacement is 8 meter. So distance traveled is 16 meter, but the displacement traveled is only 8 meter. Example number 6. A jet airplane traveling at a speed of 500 km per hour ejects its product of combustion at a speed of 1500 km per hour relative to the jet plane. What is the speed of the latter with respect to an observer on the ground? So what are we given? Velocity of jet plane with respect to the ground. We call it as velocity of plane with respect to ground. Then velocity of the combustion products with respect to the plane. So we can write what would be velocity relative VPG. VPG would be VP minus VG. VCP would be VC minus VP. Then we are required to calculate velocity of the combustion product with respect to the ground, VCG, that is VC minus VG. The combustion product and the plane are moving in the opposite direction. So equation 1 plus equation number 2. So we get VPG plus VCP. So this VP cancels and we get VC minus VG, which is nothing but VCG, the required one. So VPG, it is 500. VCP has opposite direction to the motion of the plane, so we write it as minus 1500. So the net velocity is 1000 km per hour. So velocity of combustion products with respect to the ground is 1000 km per hour. Example 7. A police van is moving on the highway with a speed of 30 km per hour. It fires a bullet at a thief's car, speeding away in the same direction with a speed of 192 km per hour. If the muzzle speed of the bullet is 150 meter per second, with what speed does the bullet hit the thief's car? So speed of the police van is 30 into 5 by 18, that is 25 by 3 meter per second. Speed of the bullet is 150 meter per second. What is the effective speed of the bullet? That is V1 would be equal to velocity of the police van and speed of the bullet. That is 475 by 3 meter per second. Speed of the thief's car is 192 into 5 by 18, that is 160 by 3 meter per second. Since bullet and the thief's car are moving in the same direction, so what is the relative speed between bullet and the car? It would be V1 minus VC, which would be equal to 105 meter per second. This is what is the speed with which the bullet would hit the car. Let us pick another example, example number 8. Two towns A and B are connected by a regular bus service with a bus leaving in either direction every T minute. A man cycling with a speed of 20 km per hour in the direction A to B notices that a bus goes past him every 18 minutes in the direction of his motion and every 6 minutes in opposite direction. What is the speed T? What is the period T of the bus service, and with what speed do the buses ply on the road? So let us see. Speed of the bus we represent by VB, speed of the cyclist VC, and VC is given as 20 km per hour. Distance covered by the bus in T minutes is VB into T. Relative speed between bus B1 plying in the same direction, so V same would be VB minus VC. Distance covered by the bus B1 relative to the cyclist in 18 minutes is V same into 18. For the bus B1 to pass the cyclist, what is required? 8 into V same, 18 into V same is equal to VB into T, and we call it as equation number 1. Now similar situations for the bus second moving in opposite direction. Relative speed of bus B2 plying opposite to the motion of cyclist and the cyclist, V opposite would be VB plus VC. Distance covered by the bus B2 relative to the cyclist in 6 minutes, it would be equal to V opposite into 6. For the bus to pass the cyclist, 6 into V opposite must be equal to VB into T. From equation number 1 and 2, 6 into V opposite would be 18 into V same. Substitute. What do we get? VB plus VC would be equal to 3 times VB minus VC. So VB would be equal to twice VC. So 2 into 20, that is 40 km per hour. What is time period T? It would be 6 V opposite upon VB, which would be 9 minutes. So the time period is 9 minutes and the velocity of the bus is 40 km per hour. Hope our two videos of one-dimensional motion part 1 and part 2 have clarified the basic concepts of one-dimensional motion. If you have all enjoyed and understood the video, you are all requested to subscribe the channel if you have not done. And you are requested to like and comment on the videos that you are observing to enhance your knowledge. Thank you. See you in the next video.